Okay, off we go. So here's picking up where we left off. So we talked about this idea of doing integrals in polar coordinates. And remember, that's just kind of a streamlined version of an argument that's actually a change of variables. And we're doing a pullback where we use the coordinate conversion formulas as a change of variables function. And the punchline is that you just have to look at slices a particular way, right? You think about these, what you might call theta slices in the r theta plane, in terms of what they look like in the xy plane. Okay, all right. So another example. This is a nice one because of how difficult the example would otherwise be. This region, this is called an annulus. It's like a ring, like this. Something along those lines. Right, so how do we do this? Now, a lot of people make the mistake of thinking that they can say, well, we'll do the integral on the large disk, and then we'll subtract the integral on the small disk. And a lot of people figure, well, blue minus purple, and that leaves the annulus we're interested in, and that would be all well and good, except for the really unfortunate fact here that this integrand is undefined at the origin and not in a good way, right? This is a fiery explosion that happens at the origin there. So neither one of these integrals, the blue integral, the purple integral, neither one of them is defined. And it's tempting to say, well, improper integrals, well, that's a sticky business, as it turns out, with multivariable integrals. So that's not something we can realistically do. So this is a really bad approach. Basically can't do it. Now, the second thing you could do, and we're absolutely not going to do this, but you could break it up into four regions like this. And deal with those four integrals separately. But those are hard integrals with square roots in their bounds. Nobody wants that either. Plus, no one wants to do four separate integrals. So also bad. So polar coordinates to the rescue. Polar coordinates makes this an easy problem because you notice first that theta goes all the way around. So 0 to 2 pi, as we previously noted. And then, okay, well, then for a given theta slice, R starts at that point, which is on that curve, which has that equation in which I can solve for R, and I get 1. Right? And then R is going to end at that point, which is on that curve, which has that equation in which I can solve for R, and it gives me 2. So super easy in polar coordinates. Now I'll give you the usual warning. Don't forget your stretching factor, right? So easy to forget this stretching factor. My personal ritual, right, to make sure that I don't forget it, and this works most of the time, but I'm highly fallible, right? But it helps me to think of, as part of my process, I always write down RD, RD theta all at the same time. I strongly encourage you to do something like that, or have some other insurance policy to ensure you won't forget that stretching factor, because this is gold, right? It's points for practically nothing. It's so easy to get those points, and you don't want to, be super mad at yourself. Right, someday, because I forgot to put this picture. I lost 4 points. Oh my God! Right, because of one little micro detail. Okay.
I have a question. Is it safe to say that if you have, we're given an equation that is somehow circular, should we
It's a little bit of an overstatement. It's not quite that convenient, but certainly it's a good instinct that circles are strongly suggestive that you might be thinking polar coordinates. Certainly if they are centered at the origin, like these are. And then there's some other versions that we're going to do in a second. You'll see some tweaks. But yeah, sometimes it's not that nice, though. Yeah. Right. Okay. By the way, look how easy the integral ends up being. Super convenient. Right? So that's a good thing. All right. Moving along, another example. This one's a little bit harder, but not so bad, really. So we have here a disk. That's this disk right here. And this says we're going to exclude all of the points that are in that disk. So green, but excluding all the ones that are also in the red, and altogether then that gives us that our domain is just this kind of solar eclipse looking thing right there. Okay. All right. So how are we going to slice that up? Well, now again, if you try to do this in rectangular coordinates, you can. You can do this in rectangular coordinates. It's going to be 3 separate integrals, and there's going to be square roots in your bounds. You could do that if you really wanted to. I don't think it's a good idea. Much easier to think about how we would do this in polar. Notice, I already got my stretching factor in there. I got those several points locked down, right? That's a good thing. Peace of mind, I won't forget it. X, of course, is easy to convert into polar coordinates, no problem. That's nothing to it. Now let's think about the bounds, starting with theta slices. This is what your theta slices look like. Remember, theta comes out of the origin like that. And so these are various theta slices. And let's think about first and last. The first one is going to be this kind of corner right there. And what's the value of theta at that corner? Now you could observe that at that point we're on both of these curves. And you can write down both of their equations, and you can then, set the one r equal to the other r, or do a little trig. You can do it that way, that's fine, no problem, and you can find what theta is, like that. Here's a cleverer way to do it, and I think it's useful to be on the lookout for this. Notice that that and that are radii of a circle of radius 1. And notice that this is a radius of another circle of radius 1. That means that this is a little equilateral triangle right there, and then, flashbacks to high school geometry, we already know that angle. Everybody see the little slick move there? It's a good idea to be on the lookout for this kind of thing. I think it's very convenient, saves you time in some instances. Keeping in mind, of course, that the angle we're looking for is clearly negative, and so this is negative pi over 3. Is everybody good? Alrighty, well, next part of the problem, let's think about for a given theta slice. Well, r is going to start at that point, which is on that curve, which has that equation, looking for r, so we solve for r, and we get 1. No sweat. And then our upper bound, still talking about r, that point, which is on that curve, and now we have a problem. We don't really have the equation for this curve in polar coordinates. Not conveniently anyway. What we do have is that it comes from this equation in rectangular coordinates, and you can convert that into polar coordinates using chapter 1 methods. And so, flip back in the notes and remind yourselves how that works, converting from rectangular to polar. This is what the punchline ends up being. And again, keeping in mind we're talking about that point on that curve, which we can now say has this equation. We solve for r, and we get that. Is everybody buying it? Okay. This example here is super cool, and I wish we had time for it, but we really don't. This is not critical. It's an optional sort of a thing. I put it in here for kind of historical interest. This is a cool calculation that got done for the first time several hundred years ago, and it's just extremely clever. And it does make use of polar coordinates, which is why I can sort of justify throwing it in here. But we don't need it. It's highly optional. Take a look at it if you're curious. right? If you want to hear an explanation of this, remember, you can always look back at my older recordings find some semester where I did do this, and you can hear as much as you like about it. But we're not gonna spend time on it here. Okay, so that's polar coordinates. What about cylindrical coordinates? What about spherical coordinates? It's going to turn out that they're strategically, practically the same thing. The geometry is a little different. The algebra ends up being a little different. But strategically, it's very, very similar. We're going to do a change of variables. We're going to use the conversion formulas, the coordinate conversion formulas, as our change of variables function. There's going to be a pullback and a stretching factor. We're going to memorize the stretching factor. And the pullback domain, we're never going to bother to actually draw because we can see everything we need in XYZ space. So for example, if I'm looking at XYZ space like here, and if I were to imagine pulling back and then doing theta slices like so, there's a theta slice perpendicular to the theta axis. Well, yeah, sure. This is what it looks like when you do a theta slice in R theta Z world, but I can also just see what that looks like in XYZ world. And so, same deal, you don't need to draw this, you can just see this. Right, so that's how we're going to proceed, and let's just, a couple of tips and tricks before we get into an example. Another bit of good news. Of our 6 different options for how to order the differentials, there's really only 2 that are worth bothering with. And the other 4, in practically all examples, if not all examples, that you'll ever encounter naturally, those other 4 options will never be better than both of these. So I would say entertain only these 2 and make your choice based on which of these 2 options is going to work best. All right, the way you're going to remember these 2 options is that dr and d theta are always together and in the usual order, and the only question is whether dz is on the outside or whether dz is on the inside. And by the way, I mean, very often I'll make the choice between which of these options to use by asking myself, would I rather solve for z or would I rather solve for r? And just let the algebra suggest which one of those is going to be more convenient. Okay, and sometimes it doesn't matter much either way. Okay, again, always put your stretching factor in at the same time that you write your differentials. You're never going to write dr, d theta, dz without needing to include an r at the same time. So it doesn't make any sense to wait on writing that r down. Right? Get it on the page, get those points on your score sheet, and then you don't have to worry about it anymore. And then our usual rules for how we find bounds. We identify the corresponding points. We identify what surfaces they're on. We write down those equations, and then we solve for what we want. Okay, here we go. So let's look at this domain here, this half ball, like that. I'm going to slice in this order right here, dz, dr, d theta, for no particular reason. I'm going to do it the other way momentarily. Let's start with this one. I've got my stretching factor in here already, so I don't have to worry about forgetting that. Right, that's a load off. I've already got some points in the bank. That makes me feel good, right? So, all right, now let's start our slicing process. And as usual, we start on the outside. Theta slices look like this, as we previously discussed. The actual cross sections are these little quarter discs, like this. And geometric appeal goes all the way around, doesn't it? Everybody see that from the picture? So 0 to 2 pi. Okay, so now we fix a value of theta on that theta slice. Let's now look at our R slices. Okay, all right. Well, yeah, so what is an R slice? R slice is a constant value of R. A constant value of R is going to be it's like a cylinder. So that's a little creepy and hard to visualize. And in this case, if I try to draw the appropriate cylinder, mess that up. Might be something kind of like that. And here's the thing: I don't need the entire R slice. I just need to know what is the R slice of my theta slice. So I'm interested in that cylinder only to the extent that it intersects the theta slice I've already got, and that intersection is just going to be a little segment like that. So that's what your R slices are going to look like. dr being on the inside of the d theta, R slices are always going to look kind of like that. And that's nice and convenient. Okay, so let's think about first and last. Well, the first one is going to be there, which is on the z-axis, where r is obviously 0. That's handy, right? All right, where's the last? Well, these slices kind of proceed along like this and keep getting shorter and shorter until the very last one is going to be a point like that. And now I've got to have to figure out what is the value of r at that point. Okay, well, you can write down a bunch of algebra, but sometimes there's, again, little geometric little bits of good luck. And in particular, notice that the value of r, the distance from the z-axis, happens, in this case, I can see from the picture, to also be a radius of that ball. And I already know that the ball has a radius of a. That means that r there is a, and thus a. Everybody happy with that? Okay. All right, so now, as usual, now we're going to consider both r and theta both to be fixed. So we're looking at that R slice of our theta slice, and on there I now want to know what are the starting and ending values of z. Well, we start there where z is obviously 0. Again, the picture sometimes makes things obvious. That's very handy. The interesting one, where does z end? Z ends on the sphere. The sphere has that equation. Now, that's not the rectangular equation. I've already converted this to the cylindrical equation. Make sure you're good with that, right? Make sure you can take the rectangular equation for this sphere and convert that to this sphere, the cylindrical equation for that sphere. All right, now reminder, what am I doing? Oh, that's right, I'm trying to find a z bound, so I solve for z, and that gives me my z upper bound. Everybody buying it? Okay, all right. See how it's a lot like a polar coordinates integral? It's just that now there are three-dimensional regions instead of two, and there's a z involved that there wasn't previously. But other than that, it's the kind of the process, the mechanics, the strategy, very, very similar. It's just sort of geometrically different. Okay, now we're going to do this whole thing over again, but slicing in the other order. So same domain. Now dr d theta dz. It just makes the geometry a little bit different. Starting with z slices. Z slices are constant values of z, right, perpendicular to the z-axis, and so I get disks. Everybody happy that these z slices are disks? All right, first and last. First one is down here where z is obviously 0, xy plane and all that. The last one is right up there at the top, where if you think about it, our z coordinate, again, also a radius of our sphere. We got lucky again. That happens also to be a radius, and so that upper bound is also A. Everybody happy? All right. Now, as usual, we focus on a z slice. Fixing a value of z, looking at that z slice. Now we've got to do our theta slicing. Well, theta slices are like this. Okay, well, yeah, but all I care about with the theta slice is how does that theta slice intersect with our z slice? And that intersection is just going to be a little line segment about like that. So there's our actual theta slice. Now again, looking at the picture, purely geometric appeal, goes all the way around. So theta, 0 to 2 pi. Is that all good? Alrighty. And again, proceeding as usual, now with theta and z both fixed. What can I say about r? Well, we start there where r is obviously 0, and so 0 is the lower bound, right? Of course it is. It's on the z-axis, so that's a freebie. It ends at that point. From the picture, I see that that's on the sphere, which again has that equation. Now here's where a lot of students mess up. A lot of students say, oh yeah, it's on the sphere again. I already found that bound, square root of a squared minus r squared. Wrong. We are not doing the slicing in the same order. You cannot copy over the bounds like that, right? Now, it's on the same surface. It has the same equation, but we are here looking for an r bound. So we solve for r, and that gives me now that as my r upper bound. So similar looking, but not the same. Sound good? Okay, good deal. Okay, so cylindrical being so much like polar, I feel like we don't need to spend as much time on this as we do on spherical coordinate integrals. So we're going to move now to spherical coordinate integrals. Same deal, change of variables, pull back, slices seen in the XYZ space. Structurally, strategically is all the kind of the same ideas. What those slices look like, though, gets a little bit weirder. Arguably, the further you go down, the weirder looking they get. I don't have the kitchen skills to make cuts of this shape, for example, right? It's correspondingly harder to visualize how a curved slice, if you will, would intersect some other surface. It can be very confusing. Here's the good news. That's not going to affect us at all. There's a very clever way around all of this, and that is to take advantage of this first tip, and that is you should pretty much always, rare counterexamples, pretty much always put your differentials in this order. It's always the same. d rho d phi d theta. That's really the only one you ever need to entertain. I would advise not only that you may always do it in this order, I would advise that you should always do it in this order, because then the geometric process, right? Theta slices, what does that look like? Phi slices of theta slices, what do those look like? All of the geometry of your process will always be the same, and that consistency is valuable and convenient. So I really do encourage that you should always do your slicing exactly in that order right there. And then while we're at it, I'll point out, and again, don't forget while you're writing down your differentials, don't forget to also write down your stretching factor. So easy to forget, so many points, free for practically nothing. Get those points on the board. Don't trust yourself to remember, et cetera, et cetera. I've said it several times already. So now, what's the benefit and why is it convenient to do it in this order? And there's a couple of reasons, one of which is the geometry of how the slicing works. So let's go through and think about how that slicing works, starting with theta slices, which we've already agreed are half planes hinged on the z-axis. That's That's a theta slice. Now we start to get worried when we're like, uh-oh, now I'm going to have to take a phi slice. This cone represents a constant value of phi because, well, angle off of the z-axis is what phi is. So this is a phi slice, and the geometry on that's going to be confusing. But keep in mind, all I need this for is how does it intersect with my existing theta slice, and how that intersects with the green. Pretty conveniently, it's always just in a little line segment like that, nice and flat and straight. So all of the scary, of the weird, of the curvature of the phi slices, no, it's just rays coming out of the origin. It's a nice simple way to think about it. Is everybody happy with that? All right, and then depending on what your solid is for a given phi and a theta, maybe you have something like this. Your lower bound for rho is just going to come from, well, what's the value of rho on that first point, and your upper bound for rho is going to come from, well, identify that last point and what's the value of rho there. So again, we don't really need to worry about these little spheres down here. It's just you just look and see what the value of rho is at your start and your end. So the geometry of the slicing is actually not that bad. Okay, let's do one. Starting with this domain. It's a ball. Not centered at the origin, right? It's centered up here on the z-axis so that it's kind of sitting on top of the xy plane there at the origin. So it's tangent to the xy plane at the origin. Playing the usual game, we're going to do our theta slicing on the outside. There's a theta slice. The cross section is kind of like this. That's a half disc. Purely geometric appeal, right? Is everybody with me? Is everybody happy with that? And purely geometric appeal goes all the way around. Right, now you just got to visualize these theta half planes as they kind of swing like a door around the z-axis. Well, you're going to get cross sections all the way along. Okay. All right, so 0 to 2 pi. All right, now we're going to fix a value of theta. But before I go on to my phi slicing, my little ritual, you don't have to do this. This is highly optional. I think this is helpful. It may or may not be worth it to you. Suit yourself. I like to redraw the theta plane and the intersection in such a way that I'm looking right at it. Whereas previously, this theta plane that we have here, I'm kind of looking sort of a stance at it. I'm looking kind of from a side angle in some sense. And here's what's weird. If you think about, for example, this direction right there, that's actually horizontal. But on my page, it looks like it's pointing somewhat downward. Now, that's just a relic of the fact that we're trying to use a two-dimensional picture to think about a three-dimensional thing. And okay, so that's something you can deal with, and you could just kind of keep track of that in your head. But I find it somewhat satisfying to just, redraw it, and then now the thing that we know is horizontal actually looks horizontal. It's just a little bit friendlier. Suit yourself. Again, highly optional. Okay, so that in mind, here's one of our slices, and we are going to be doing phi slices of that. Remember, our phi slices are represented by rays coming out of the origin. And so let's think about first and last, and the first phi slice is going to be the one that's straight up, where phi is 0. And progressing greater and greater values of phi, and you keep getting these slices, and that you notice that they get shorter and shorter. The closer you get to horizontal, the shorter and shorter they get. And keeping in mind that this ball is actually tangent to the XY plane, this cross-section is tangent to the horizontal down here, and that means that the last slice is actually going to be straight horizontal. Anything that's at a higher elevation than that will have an intersection. Anything that has a lower angle than that, total swing and a miss. So that last slice, pi over 2. Yeah.
Yeah, in the case that it's a bit higher, not like tangential to the
Yep.
How would you go through the intersection?
How would the what now?
How would you walk through the intersection?
Oh yeah, we're gonna get to that. Yep, right. Yeah, okay. So so our process is right. We got to think about first and last, and then go to fixing a slice and etc. Yeah. Okay. So there you go. Our phi bounds are 0 to pi over 2. Okay. Now we're gonna fix phi and theta. So let me scooch down here. We're going to fix phi and theta. We've got those bounds worked out. So we're fixing phi and theta, looking at a particular phi slice. Let's think about starting and ending for rho. Well, we start there. That's at the origin. That's obviously 0. Again, you get really lucky sometimes. Boom, write it down. If it's that obvious, no explanation required. There you go. But where it gets interesting is the upper bound. So that upper bound, well, it's on this curve. Where did that curve come from? It's really easy to forget where that curve came from. Right? Remember, we're just looking at that point, which is on that curve. But remember, that is really that curve from our actual three-dimensional picture. So the point in question there, in fact, is a point that is on the sphere. And so you can take the good old, regular old rectangular equation of the sphere. Now, of course, we're going to need it in spherical coordinates, so you do have to do the chapter 1 conversion to get that in spherical coordinates. But that's the equation of that sphere. Make sure you can do this process, converting the rectangular equation of the sphere to this spherical equation of that sphere. And then, as usual, let's see, we're looking for a rho bound, so we solve for rho, lucky break already done, and there's your upper bound. Everybody on board? Okay. By the way, again, reminder, don't forget your stretching factor. Can't emphasize that enough. Okay, so notice how we use the pictures dramatically, right? And we really need the pictures on this. And remember, this is not just as a tool to help you get the right answer. This course is not about answers. It's about reasoning and ideas and communicating thought processes, right? So you are going to have to give me some sort of evidence of what your thought process was. And I am not aware of a reliable and therefore mathematically valid strategy for making arguments for what the bounds are that doesn't use pictures. Like a purely algebraic argument, I don't think there is one. Now, there are methods that will often give you the right punchline. That's not mathematical reasoning, right? We need reasoning that shows that this is right, not good guesses and you're willing to take the chance and that kind of thing, right? So we need something that actually is mathematically meaningful. So I think it's got to be a geometric argument. If you're going to present a geometric argument, you got to have a picture. So this is practically required. For all intents and purposes, it's required. And so being able to draw a reasonably good picture is going to be really important. So how do you do that? Well, a couple of easy, obvious points. Don't make it postage stamp size. It's going to be hard to read. Your picture is going to get muddled and messed up the more you add to it. So make it nice and big. Give yourself plenty of space. Don't expect you're going to do it all at once. You just see the picture in your mind and just draw it and it just comes out just perfect. Practically no one can do that really well, right? When I make good drawings, that's not my first one. My first drawing was terrible, but I kind of learned a little something about the shape after, from that first terrible drawing, and then that helped me make a better second drawing. And then that helped me learn some things about the shape, and that helped me make a better third drawing. And repeat as many times as is necessary, right? Again, it's a good idea to kind of try to do it in stages. Keep in mind, on the exams, you have scratch pages at the end. Use those to scratch, draw, and kind of help yourself figure out how to make a good drawing, and then draw the good one on your paper. Does that make sense to everybody? Okay. Oh, by the way, yeah, and also there's stuff to know. This is not just a matter of talent, right? I mean, I guess maybe there is such a thing, but there's stuff to know. Make sure you know what there is to know about how to make good drawings. It will really help a lot. I've already documented in those recordings on my YouTube channel everything that I know about mathematical drawing relevant to Math219, relative to multivariable calculus. Right? So I think there's some good ideas in there. I hope you'll find them useful. But make sure one way or the other, whether you use my recordings or somebody else's or a book or whatever, don't just go in there and wing it. Right? There's stuff to know. Use the stuff that there is to know. And then last observation, I got better with drawing by quite a bit by practicing. I think it's a skill. I think it's like technique, like learning how to play the piano. You cannot just read a book and then instantly be an excellent pianist. You got to get your muscles to coordinate and figure out how to make your fingers do what your brain is telling your fingers to do, right? And I think it's the same with drawing. And so, maybe dedicate a little time to practicing drawing. Consider every homework exercise as an opportunity to practice your drawing so that when you get to the exams, you'll be more likely to have good drawings that help you see what you're doing, that help you communicate your thinking, and thus help you get points. Okay, another example. Another ball. Looks something like this. This one's offset also, but this time in the Y direction, right? Again, we're going to do the slicing in the usual order. Again, don't forget your stretching factor. Super easy to forget. Go ahead and get those points. Get them on the board. Don't leave it to chance. Starting with our theta slicing. Now, geometric appeal. You think about what this ball looks like. This ball is offset to the right. The center is moved over to the right by exactly the same amount as is the radius. So this is tangent to the XZ plane at the origin. Right? And so again, because it's tangent, that means that every value of theta a little greater than 0 is going to have an intersection kind of like this, and every value of theta that is that's not drawn well. Every value of theta that is, you might say, to the left of the x-axis there is going to be a swing and a miss. There's nothing over there. Right? Does everybody buy it? Now this is a geometric appeal. Got to see it from the picture. So there's that, yeah. Likewise on the other side, right? Sort of the last. These are hard to draw, aren't they? The last slice that's going to work is going to be where we're at pi. Anything that's beyond pi, again, pointing off in the sort of to the left, in the negative y direction, going to be a swing and a miss. And so our theta bounds 0 to pi. What do you think? It's all from the picture. It's all geometric sort of argument. That make sense? Okay. All right. Okay, so right, so one of my cross sections is going to look kind of like that. I am again going to take my slice and redraw it. I just find this a little bit easier to visualize. Suit yourself. This is optional. You don't have to do it like that. But now let's think about values of phi. And phi slices, again, are kind of rays coming out of the origin, like so. And let's think about first and last. And, well, this cross section is a disk. Claim it's tangent to the z-axis because in the picture here, it's part of a sphere that is tangent to the z-axis. Everybody buy that? Okay. And therefore, again, first and last. First is going to be 0, from which those phi slices will grow bigger and bigger until they start going smaller and smaller, and eventually to disappear at pi. Also 0 to pi. Again, right? You got to see it in the picture. Okay. All right, and then let's see. Whoops. Again, we now fix a slice of our slice. So phi and theta now both fixed. And let's think about rho. First and last. Well, the first is at that point, namely that point. Well, that's the origin where rho equals 0. Again, freebies, take them when you get them. Gotta love it. Last is going to be that point, which is on that curve, which don't forget is actually that curve. Namely, it's on the sphere. Being on the sphere, well, here we are again. Knowing the radius and the center, you can write down the rectangular equation, and then you got to be able to convert that rectangular equation to the spherical equation for that sphere. This is a different sphere. It's got a different spherical equation. Make sure you can do this, right? Old chapter 1 stuff. There's stuff to be dealt with and, tricks to be taken advantage of. So, again, remind yourself of all that stuff from way back when. And again, solving for rho gives you your upper bound. Everybody happy? Okay. So one more example. Now this one is, there's some math to this one, and I think this is a good one to go through in terms of the details on your own. The purpose of me including this is to focus on a little point of art and geometry, because this is a hard region to draw well. I don't really have any good drawing of it. It's just too weird. We've encountered hard stuff to draw before, and I kind of, was frustrated by I don't know how to draw this, and therefore I don't know how to draw slices of it. This is not that different. What we have here is this ball, and that's a ball, but wait a second, this other one, greater than or equal, not less than or equal, that means we're looking for what's outside of this ball. Right, so inside the green, outside of the red. Everybody see that? Alrighty, well, gosh, how am I going to draw that? And here's my, that's clearly wrong, right? I mean, if you imagine taking a spherical, a convenient little metaphor is to imagine you've taken a melon baller to a melon and you've got a little ball of melon there, right? But then you take your melon baller and you scoop out a spherical sort of divot out of the bottom of it. Well, there's going to actually be kind of a rim around like that. And there's actually melon here. And if you poke in to where the melon, you'll eventually poke out of the melon and into the cavity, and then as you continue to poke further, you'll get back into, there's more melon on the back side there. Right? So how do you draw that without it looking, I don't. That's hard. I don't know what to do with that. Right? Okay. So here's the little artistic hack I want to point out. First, a little bit of terminology. I'm going to refer to our solid as being an intersection. It's a little bit of an abuse of the term, but not quite, not really. We're looking for points that satisfy two requirements. Inside of this ball and outside of that ball, it's kind of an intersection of sorts. I'm going to call it an intersection. We need to take cross sections of it. Right? I need to think about how do I do that cross section of that intersection. So here's the clever observation. I can look at the individual cross sections. Right? So for example, you take this ball. Its individual cross section is going to be some disk. Like that. That's easy. That cross section's nothing to it. Then there's also this ball down here. Its cross section is going to be, something like that. And the big point, the big realization to make is that the cross section that I am looking for, the cross section of the actual intersection I care about, is just the intersection of those two cross sections. And here I've got those two cross sections drawn better, and here's how they intersect. Again, keeping in mind that we mean outside of the bottom one, but inside of the top one. The intersection of those two cross sections is just going to be something like that, which is like a claw, like an eagle talon or something like that. Does that make sense? Okay. I think it's a cool little, convenient little, artistic little trick. I encourage you to take advantage of that if it might be helpful. I think it's particularly neat to notice it's actually easier to draw the cross section of this weird solid than it is to draw the solid itself. The solid itself was really hard to draw. Its cross sections ended up actually being easy to draw. Okay, a bunch of other details. Make sure to read that on your own. And I'm just going to end with a real quick reference. I know we're short on time. I have 2 minutes. I just want to remind you all of a theorem from single variable calculus. We'll pick up from here next time. But there's this odd integral theorem. If you have an odd function, such as odd powers of x, in particular, a minus sign in causes a minus sign out. Y'all remember odd functions? It turns out that if you have an odd integrand, and if you integrate from negative a to a, in other words, if your domain is symmetric, that integral is equal to 0. And you don't have to do any integrating. No antiderivatives, no trickery with substitutions or whatever. If you simply know the integrand is odd and your domain is symmetric, negative a to a, poof, the integral is equal to 0. Comes up here and there in single variable calculus, but for whatever it's worth, it comes up enormously in multivariable calculus, and it comes up enormously in real-world physical computations, such as I did in my physics major, and such as most of y'all are going to be doing in your engineering majors. The multivariable version of this is going to end up being one of your most commonly used integration techniques. More on this on Monday. See y'all later. Have a good one. Don't forget about attendance.